All right, hey, welcome to week 44 of Chill Kernel Hacking for Fun. This week we are doing copy on write fork. In the previous weeks, I've been working through all these exercises in lab 4. I implemented the basic system calls for environment creation, which now allows processes to create new processes. And last week, in week 42 actually, I fixed a bug in this, and I also investigated a few details related to multi-core support with scheduling and stuff like this. But now we're back on track. Now we are back following the lab, and let's just get into it. I'm just going to go ahead and read through a bit in this. So fork, as mentioned earlier, Unix provides the fork system call as its primary process creation primitive. The fork sys call copies the address space of the parent to create a child. xv6 implements fork by copying all data from the parent's pages into new pages for the child. This is the same approach as dumb fork, which is what was above. This is kind of the most naive way to implement this. It's not optimized and does a lot of the copying. It does all of the copying up front. It's expensive. Copying is expensive. However, a call to fork is frequently followed by almost immediately a call to exec in the child, which replaces the child's memory with a new program, which is what a shell typically does. In this case, the time spent copying everything is largely wasted because the child process will use very little of that memory before calling exec and then wiping out all of the memory in its process. So for this reason, later versions of Unix took advantage of hardware to allow the parent and child to share the memory mapped into their respective address spaces until one of them modifies it. I'm assuming by hardware support, I guess we need support in the page tables for this. I'm thinking that the write protect bit, or basically just readable, and a read write bit, so the OS can detect when a write is happening to a page. Okay, copy on write. So share the memory between these two processes until someone modifies it. This technique is known as copy on write. To do this on fork, the kernel would copy the address space mappings from the parent to the child instead of the contents. So basically just the page table entries, but they're going to point at the same physical pages. At the same time, mark the now shared pages read only. It needs to mark all of them read only. I mean, it needs to mark all of them that were writable to now be read only. Pages that were previously read only can remain read only. They don't participate in copy on write because they're not writable. When one of the two processes tries to write to one of these shared pages, the process takes a page fault. Either in the parent or the child. At this point, kernel realizes that the page was really a virtual copy on write copy, and it makes a new private writable copy of the page for the faulting process. In this way, the contents of individual pages aren't actually copied until they're written to. This optimization makes a fork followed by exec much cheaper. In the next piece of the lab, we'll implement a proper Unix-like fork with copy on write as a user space library, which is interesting that we're doing it this way. Implementing fork and copy on write support in user space has the benefit that the kernel remains much simpler and thus more likely to be correct. That is interesting. It also lets individual user mode programs define their own semantics for fork. A program that wants a slightly different implementation, for example, the always copy version can provide their own. That's interesting. That's an interesting design decision. Leaving it up to user space to actually implement how the fork is done. Yeah, there are probably, maybe, I mean, there's probably trade-offs associated with that. But basically, we're basically moving fork into the libc rather than as a syscall. And maybe there's a bunch of trade-offs, like it requires exposing a bunch of syscalls to user space that in practice in a production system we wouldn't really want to expose, because actually we do expose quite a few things here. For example, sys set status, like that's a really direct access to kernel data structures. I'm not sure a production OS would really want to expose that kind of system call. So there might be certain limitations. Yeah, there might be certain like limitations with this approach, and it might conflict, which might mean that it doesn't work for all use cases, and in some use cases, or maybe most production use cases, you need to move this into the kernel so that you don't need to expose so much surface area of the kernel. But anyway, okay. User level page fault handling. A user level copy on write fork needs to know about page faults on write protected pages. So that's what you'll implement first. Copy on write is only one of many possible uses for user level page fault handling. And so this is interesting because actually Linux also has this. I believe it's called user fault FD. And it allows page faults to be bubbled up to user space to allow it to decide what to do with them rather than only being handled in the kernel. I just want to make sure I understand this first sentence. A user level copy on write fork needs to know about page faults on write protected pages because, so just to kind of sketch out what the user space fork implementation is going to do, we already have this dumb fork thing which kind of does it, but it does this exo fork thing to kind of just to make a new process that's kind of empty and doesn't really have anything in it. We need to have some way to share the mappings, but then it's talking about, I guess I don't fully understand exactly what we would do with that at this moment, but that's why I'm taking this class, so I can learn about that. Yeah, that we'll see. I'm curious how that's going to work. It's common to set up an address space so that page faults indicate when some action needs to take place. For example, most kernels initially map only a single page in the stack and allocate and map additional stack pages later on demand. And page faults happen when the program goes off the stack. And so we're kind of structuring memory such that basically the page fault is a bit of a callback. When some kind of event happens that the kernel needs to handle, it structures memory such that a page fault will happen then, and the kernel can get the callback and handle it in a kind of asynchronous way, or like a callback approach way rather than polling. Okay. Kernel must keep track of what action to take place when a page fault occurs. So page fault can occur for many different reasons, and we need to know what to actually do because we're kind of multiplexing all sorts of stuff into a single entry point, which is the page fault. Fault in the stack region will typically allocate and map new physical memory. Fault in the BSS, allocate a new page full of zeros and map it. That is interesting. Yeah, the BSS doesn't need to exist on program boot up. It can be faulted in as needed. System with demand page executes a fault in a text region will read the corresponding page of the binary op disk. In the text region specifically, it needs to, yeah, it can't like, I was just thinking about, there's something about swapping and swapping from disk or anonymous pages. I think there was something along the lines of only anonymous pages are eligible for swap, and text pages that are backed by disk don't go in swap. Something like that. Okay, anyway. A lot of information to keep track of. Instead of taking the traditional approach, you will decide what to do about each fault in user space. That's interesting. Where bugs are less damaging. This design has the added benefit of allowing programs great flexibility in defining their memory regions. You'll use user level page fault handling later for mapping and accessing files on a disk-based file system. I don't totally know what that means right now, but hopefully I will understand this later. In order to handle its own page faults, a user environment will need to register a page fault handler entry point. Ah, I see. Yeah, I was kind of wondering how this is gonna work. Because the user space seems like it needs to have some kind of callback that the kernel is going to execute, almost maybe like a signal handler or something like that. That is actually interesting. So page fault's going to happen. User space is going to register with the kernel, presumably, and pass in some kind of function pointer maybe, or an entry point. And then later when a page fault happens, we're going to, it'll trigger the interrupt and trap handling infrastructure. But I guess we're just going to kind of revert and defer to user space and return to user space, but switch execution to hit a different point than the original saved register state, which is interesting. And then we need to have some way to divert execution back to the original instruction that triggered the page fault. But okay, user environment registers its page fault entry point via the new syscall. This sys envset page fault up call syscall. We have added a new member to the env structure to record this information. Let's take a look. Where? Oh, what? It's here. Okay. Yeah, here it is, exception handling. And it's a void pointer. Yeah. So implement the sys envset page fault up call syscall. Be sure to enable permission checking when looking up the environment ID of the target environment, since this is a dangerous system call. So that's interesting. So apparently when you make the system call, you can actually choose which process you want to listen for page faults on, kind of. Like you can say, I'm not just listening for page faults on my own process, but I can also listen for page faults on my children, which I guess that makes sense. Okay. So, okay. Up call. Okay, so here we are. And it returns an int. So it'll be, oops, it will be something like, env set up call, and it takes two arguments, one of which being a void pointer. Okay. Right. What else does this say? That's it. Okay. Set the page fault up call. Page fault up call. That's a very interesting. It's an up call. I guess the word up call comes from the fact that usually if you visualize these things, the kernel is this kind of lower layer and the application sits on top of that. And so syscall is calling down, but then here the kernel is going to call up into the process. Set the page fault up call for env ID by modifying the corresponding struct field. When env ID causes a page fault, the kernel will push a fault record onto the exception stack. The kernel? Okay, I don't know what that means. I know the CPU pushes data on some stack, but it says the kernel will push, then branch to func. So the kernel will take that data and then maybe forward it somewhere. It needs to pass, presumably it needs to pass that data to user space somehow. So not quite sure about that one. Okay. So return 0, what do we do? So we need to d to env, and we're passing, yeah, the pointer true. Nope. Error. Okay. That's how this works, right? It returns error code. If error, return error. Otherwise, we got, and then env up call equals func. Success. Errors are bad env. And that's the one that's returned here. I think that's it. I don't think I really have a way to run this yet. So, but I think that's all it takes. It's quite simple. Just look up the environment, turn on permission checking, set the struct member, and also add the dispatch. Okay. So that's 8. Impl sys env set page fault up call. Cool. Okay, that was not so hard. Let's keep going. Normal and exception stacks in user environments. Interesting. During normal execution, a user environment in JOS will run on the normal user stack. Wow. Okay, now we are getting into very interesting OS design territory with all these different stacks. I actually am not super familiar with this really, but here's what I do know. In Linux, each thread has its own stack. And that's pretty much the main stack. What I don't know actually is how signal handling works. Because I think that's the main other way to kind of have kind of a concurrent execution on a single thread. And I don't know what stack a signal handler runs on, actually. So it runs on the normal stack. It's ESP starts at use stack top, and we go down. Pushes resides on the page between stack top minus page size and stack top -1 inclusive. When a page fault occurs in users mode, the kernel will restart the user environment running a designated user level page fault handler on a different stack, namely the user exception stack. It will make the kernel implement automatic stack switching on behalf of the user environment, in much the same way that the x86 processor already implements stack switching on behalf of JOS when transferring from user mode to kernel mode. So what happens there, user mode is executing and it does a synchronous exception or trap or system call instruction, or an external interrupt comes in. The processor automatically switches stacks onto the stack pointer pointed to in the TSS descriptor, or the TSS entry or something, right? And we're going to do the same thing. It's going to be running in user space. It's going to hit a page fault, and we reroute it and reset the stack pointer somewhere else. But we need to have a different stack somewhere. That's interesting. JOS user exception stack is also 1 page in size, and its top is defined to be at virtual address UX stack top. So the valid bytes are from UX stack top minus page size through that. While running on this exception stack, the user level page fault handler can use JOS's regular system calls to do things, apparently. Which is interesting because usually I'm just kind of always comparing this to signal handling. When you're writing signal handlers, there are all sorts of things you need to be careful of, and all sorts of things you can't do because they might conflict. With I guess it's other threads maybe, and so because we don't have threads, maybe it's not such a concern, and therefore this kind of signal handler looking thing can do anything it wants. Could be, yeah. That's a question for me. Why, like, what's the deal with async signal safety, which is the name of all those restrictions when you're writing a signal handler? But I mean, I'm guessing threads are a major issue. Also locks, like there's all sorts of issues with locks, I guess. Like if you allocate memory inside of a signal handler, you can deadlock maybe. Something like that. Anyway, okay. We run on this separate user page fault handler, and we can do arbitrary stuff to fix whatever problem caused the page fault, including mutate memory mappings, do all this stuff, which is kind of cool to be doing from user space. And it's because we expose such low level detail to user space. Then the fault level, and the fault handler returns via an assembly language stub to the faulting code on the original. So that's interesting. When the user level fault handler returns, it doesn't need to do so via a system call, maybe, or probably. It can just, it needs to know where to jump back to. I'm not sure what else there is to do, but at a minimum, it needs to reset the stack pointer to where it used to be and jump back to the original faulting instruction. Each user environment that wants to support user level page fault handling will need to allocate memory for its own exception stack. Interesting. So you need to bring your own stack. That is interesting. But then how do you... Oh, I see. Okay, I think I understand. So what's going to happen is that the fault is going to happen in user space. It'll trigger the page fault handled by the kernel. The kernel will then upcall back into user space and start executing this function. But based on this, I think the first few instructions in that function are going to be responsible for switching the stack to the exception stack. I was kind of under the assumption that the kernel would actually do this automatically, but I'm not sure. Because otherwise, user space is going to need to communicate to the kernel where the exception stack is, and we haven't seen that so far. You will now need to change the page fault handling code to handle page faults as follows. We will call the state of the user environment at the time the trap time state. If there's no handler registered, the kernel destroys the environment with a message as before. Otherwise, sets up a trap frame on the exception stack that looks like a struct uTrap frame here. The kernel then arranges for the user environment to resume execution. With the page fault handler running on the exception stack, you must figure out how to make this happen. That is interesting. So it seems like the kernel actually needs to be writing a bunch of data into memory, into user space memory. But I'm still not sure how it knows where to do this. Because so far we've advertised user space has a way to communicate or advertise where its handler is. But not the exception stack so far. Okay, you must figure out how to make this happen. Fault VA is the virtual address that caused the page fault. If the user environment is already running on the exception stack when the exception occurs, then the page fault handler itself has faulted. Wow. In this case, you should start the new stack frame just under the current TF ESP rather than at UX stack top. You should first push an empty 32-bit word, then a struct trap frame. Okay. Wow, these are a lot of details. To test whether this is already on the exception stack. Basically, to test whether the program was already executing the page fault handler, check whether it is in this specific range. Implement the code and page fault handler required to dispatch page faults to the user mode handler. Be sure to take appropriate precautions when writing into the exception stack. Okay, I have a feeling we're going to need a Miro board, just some Miro action. Okay. Be sure to take appropriate precautions when writing into the exception stack. What happens if the user environment runs out of space on the exception stack? That means there's going to be a page fault, possibly. And here's where I don't quite know. Is it a general protection fault or a page fault? That happens when okay, I'm just going to ask ChatGPT quickly because I could look it up, but I kind of don't want to take all that time. So when on x8 86 32, when a user process writes to, is it a page fault or a GP fault? Page fault, okay. GP fault occurs for violations of protection rules unrelated to paging. Accessing privileged instructions, violating segment limits. Interesting. Okay, page fault occurs due to invalid or unmapped memory access. GP fault, other protection violations. But accessing a kernel-only memory from user space is a GP fault, though. Even though that is a violation of the page table permissions. Okay, I will just assume that's true. Okay. So I don't actually know what those precautions might be, actually. The precautions might be using some of the functionality that we previously implemented that queries and checks a range of memory to see if it's safe to access. We did that a long time ago, actually, but we might need to call that maybe just to see if it's safe. So thanks for the hint, exercise 9. So I guess let's just begin. Page fault handler. Okay, right. So we're in the page fault handler, which just to refresh is called here. So, right, we actually don't handle that many different kinds of traps so far. A trap happens and it has a trap number. We dispatch to either the breakpoint or the page fault or our custom interrupt, which is the syscall handler. And most of the time we've been internally dispatching within the syscall handler, but now we're kind of coming back a bit higher level and working on the page fault handler. I also just remembered that I don't have the timer running. I'm going to take a 20-second break to stand up and stretch. Be right back. Okay, cool. Page fault handler, let's just, okay, this is a massive comment. What does this thing actually do, even just right now? It also might be good to bring up my Intel manual at this point. Okay. Reference, I want to find page fault. Where is it? Full fault. Okay, well, that's way too fast. Did I miss it? This thing is... $14. There we go. Okay. Indicates that with paging enabled, the processor detected one of these conditions. Present is not set, so it's not even, the mapping is not active. Permissions, write to a read-only page. Instruction fetch. The contents of the CR2. I was trying to, yeah, that's what I was trying to look for. So what, and this documents what happens when a page fault happens. There is an error code. It's pushed on the stack. Provides the page fault handler with 2 items of information to diagnose the exception and recover. An error code on the stack with some kind of format. The contents of the CR2 register. So it's, okay, this is like very long distance, but there's 2 pieces of information. One is the error code on the stack. The second is the contents of CR2. Load CR2 with the 32-bit linear address that generated the exception. Linear address. Linear, in this case, I think it just means virtual. Like the linear thing is mostly like when you have segmentation, that results in computing a linear address, which then has a one-to-one physical mapping usually when you have segmentation going. But with paging, everything, all of these virtual operations are in the linear space, and then that undergoes a translation to resolve to the physical address. Okay, so it's a virtual address. Page fault handler can use this address to locate the corresponding page directory and page table entries by parsing the page tables in software, presumably. Another page table can potentially occur during execution of the page fault handler. The handler should save the contents of CR2 before another fault can occur. That is interesting. Otherwise you lose it. So you need to stash it away. If a page fault is caused by page level protection violation, the access flag is set when the following. Interesting. So it sets this bit. The behavior of processes recording the access flag in the corresponding page table entries. Well, wow, it's undefined. So it's in the page directory entry, that's defined, but not in the page table entry. Save contents generally point to the instruction that generated the exception. Okay. Okay, this is so detailed. Okay, this is so detailed. So detailed, okay, wow. Edge cases galore. Yeah, I would not really want to be a CPU designer needing to think about all this crazy stuff. Processors update CR2 whenever a page fault is detected. If a second fault occurs while an earlier page fault is being delivered, it'll override it these. Okay, so it's just restating. And we get a bunch of information within this 32-bit word about the page fault. Was it caused by present bit? I mean, it basically is kind of close, it seems, even to a page fault entry layout, actually. Okay. That was quite detailed, but now I have much stronger foundational understanding of what's happening here. So the page fault handler happens, we can read CR2 and save it off just like the manual told us to. We save it into a local variable, which is declared up here for some reason. Okay, fault virtual address, right? Handle kernel mode page faults, your code here. If it came from user space, do a bunch of stuff in the if statement. Or, oh wait, no, what Laffy code? This is, oh wait, okay, I was wrong, no. This and 3 thing just masks out the privilege level, and then it returns the privilege level. And in this case, it's 0, which means kernel mode. So therefore, if you come down here, that's where the user mode page fault handling is. We've already handled kernel mode exceptions. So if we get here, the page fault happened in user mode. Call the environment's page fault upcall if one exists. Set up a page fault stack frame on the user exception stack below UX stack. Oh wait, that is, oh okay, I see. So I was asking earlier, how does the kernel know where this exception stack is? And the answer is that it's hard-coded. If we go out to our memory layout, stack top, it's hard-coded, user exception stack. The normal stack is a bit lower, but the user exception stack is right at the top of user memory. Okay. That makes sense. Set up a page fault stack frame. But user space is responsible for mapping that, right? Needs to allocate its own memory for its exception stack. So that's so it needs to handle that. Then we can just assume it's there, but we also need to handle what happens if it's not, I suppose. Okay. Page fault upcall might cause another page fault, in which case we branch to the page fault upcall recursively, pushing another page fault stack frame on top of the exception stack. Trap handler needs 1 word of scratch space at the top of the trap time stack in order to return. In the non-recursive case, we don't have to worry about this because the top of the regular user stack is free. In the recursive case, this means we have to leave an extra word between the current top of the exception stack and the new stack frame, because the exception stack is the trap time stack. Okay, I don't totally get these details, but I think I will get them more later. Oh, the music turned off? Okay. There's no page fault upcall. So before I even get going, so I'm just going to go ahead, document a few thoughts. So there's a bunch of stuff. There's the basic functionality, but then we need to handle recursion if user PF handler faults. There's also this question of defensive coding for the kernel when writing to the exception stack. Kind of hinted that we need. Oh, no, it's not that one. There's no page fault upcall. The environment didn't allocate a page first exception stack, or can't write to it, or the exception stack overflows. Okay, if any of these things happen, if there's no page fault upcall, if the user didn't allocate a page, or can't write to it, or all these things happened, destroy the environment that caused the fault. Note that the grade script assumes you will first check for the page fault upcall and print the user fault VA message below if there is none. The remaining 3 checks can be combined into a single test. Okay. Hints, member assert and end run are useful here. Change what the user environment runs, modify the trap frame. TF points at kernel. Okay. So we already have this destruction code. Okay. Wow. That's my question. Is the zero upcall function pointer zero initialized actually? And alloc. Yes, clear the page fault handler until user installs one. Good. That's that's our sentinel to know if it's set or not. So, check func pointer is there. Check other 3 tests. No exception stack or unwritable or stack overflows. So we have a bunch of checks that we're going to do. At some point, we're going to need to call into the func pointer and error handling. If things did not work out, too bad. Okay. So we do a bunch of checks. Then we need to prepare the exception stack, but safely. Set up a stack frame on the exception stack below UX stack top, and then branch. Branch. It's kind of like a return or a jump. Okay. And there's all this stuff. It's one word of scratch space at the top of the trap time stack. I want to understand that better. Where do I find PF entry? .s PF entry. So this is technically a little bit later, but this is the assembly stub that receives execution. So apparently there's actually a single well-known, you don't just pass it a random function point, like a C function pointer, you pass it specifically this assembly stub, which then reroutes and jumps to this thing. I see. Kernel switches our ESP to point to the user exception stack if we're not already on the user exception stack. There was a blank word on the trap time ESP. Okay, so here's how it works. Kernel diverts execution to the entry point, which is right here. There's a small stub which passes off to the C page fault handler, which is in this call. That eventually returns, and now it's time to switch back to the original thread of execution before all of this handling happened. Let me do some push ret techniques or whatever. Okay, apparently this is hard or whatever. Okay, but that's coming up. That's not what we're doing now. Okay. So I'm going to... I kind of feel tempted to make that a fail. So if not, what do I have? Oh, cur end, right? Cur end. Up call. To fail. The grade script assumes you will first check for the page fault upcall and print the user fault VA message below if there is none. Okay. So there's that. And then I need to do all these other tests. But 20-second break. All right, be right back. What's the first one? The kernel didn't allocate a page for its exception stack. So we need to query the page tables for this value. I'm just thinking about what... I guess cur env still simply points at the thing that's running right now, the process that's running. And so we can just do a, is it page lookup? I kind of always forget these APIs. I'm thinking Page lookup is probably the one. Want. Or page dir walk. Maybe page dir walk. But is that a publicly exposed function? Yes, it is. Okay. So it's actually more like this, and I'm pretty sure page dir walk can handle all these unaligned things, hopefully. Or maybe not. Maybe page lookup is just a bit safer to use, although it just directly passes in. Okay, it's a thin wrapper. But actually, yeah, no, wait a sec. I think this handles it just fine. The unaligned nature of it, because it doesn't need any of those lobits. It doesn't really care. It just gets the directory index and then the page table index. Yeah. Okay. And false. We do not want to create something. Okay. Then we get all these things. If the allocation fails, it returns null. What? Then returns null. Yeah. Okay. So if page wasn't even allocated, then we do that. Or it's not writable. Or the exception stack overflows. How to test? Okay, I don't know if exception stack overflows. That would mean maybe a stack pointer is pointing a little bit below UX stack top. I'm just gonna, but so user space is running. Usually the stack is going to be all the way down here. So that's the normal case. So the first time the page fault happens, the stack will be pointing down here. You know, the one thing I'm a little bit unsure what to do is with the stack pointer with ESP. But this kind of says what to do. Okay. Otherwise, set up a trap frame. And then, yeah, do some stuff with the ESP or UX stack top, do all this stuff. Push the error code, push the fault VA, and then point ESP there. I think that's what I need to do. So yeah, ESP then gets pointed. Some data is written onto the exception stack. ESP is pointed there. And then under normal circumstances, well, I guess even with a non-recursive thing, so even if it just happens once, it's possible that this handler could use so much stack space that it falls off the end of the stack. And ultimately, what's going to happen is it's going to page fault from user space in this region. And I think that's how we test. We need to test if the fault VA, if we faulted on trying to access something here, basically. I believe that's the check. If fault VA is greater than equal to U stack top and fault VA is less than U stack top plus page size to fail. Maybe just do this equals X. Did overflow exception stack did overflow. Okay, just to give that some naming. Yeah, if the fault VA is in this region, pretty sure that's what that is going to mean. That means user space just did so much stuff, it went off the end. Or we recursed so much, which caused user space to go off the end. Yeah. Typo. Okay, so I think that's the tests. And then now do sig tests. Then prepare the exception stack, but safely. So then set up a page fault stack frame on the user exception stack directly below UX stack top. It would be pretty nice if I could just copy an existing trap frame. Start of struct push regs End of struct push regs. Push reg. Ooh. Trap frame. So we have the trap frame. And for push regs, I'm just gonna put all this stuff here so I can just see it all at once. So it's saying that this thing needs to look like this. Okay. So we got our trap frame, and our struct's gonna be in memory. It's gonna be in this order, going up in memory. And this is also going up in memory, so we kind of need to flip it around, but it's like, but I think it looks how I want it to look. EDI, ESI, EBP, yeah, this is all aligned. EDI, ESI, EBP, ESP, EBX, EDX, ECX, EAX. So that is very simple to just copy over, I believe. We have a couple of these extra things. Trap time ESP, trap time E flags, trap time EIP. Where does that come from again? It's from here. So I think we might need to, So I think there's a couple ways I could do this. One way would be to really just do just do memory, just do simple memory writes, and it just, yeah, into the appropriate memory slots, which to me feels a little bit weird. I mean, yeah, there's this U trap frame, which seems like the whole point of this. So yeah, I think the actual way to do this is to construct a U trap frame and then copy that into memory. Right, yeah, that's clearly the solution here. And it looks, does it look exactly like it should? So U fault at the bottom, TF error, a push, regs, EIP, E flags, ESP, perfect. So yeah, that's obviously what we're going to do. Struct U trap. Does this work? Ooh. Okay. I'm missing. Okay. So that does seem to work. Cool. Okay, so we're going to construct the U trap frame equals, okay, it's right there. So just one by one, I'm just kind of debating TF fault VA. You can do this syntax, fault VA, TF error, here's the part where I wish I had Clang format configured, which I never bothered to set up. UTF regs. This is my initial way that I can think of to do this. Maybe there is even a cleaner way, but I'm going to construct this thing. It's a packed struct, so no worries about padding. And then I need to write this into memory. At a specific place. I need to write it directly below so it'd be a pointer dest u trap frame equals use x stack top minus size of u trap frame. Oh, oops. And then it's just simple. It says simple as this equals this, I believe. We just, we compute. It might even be possible to one-shot this and directly, it might be possible to even I don't know. See well enough. I'm going to ask ChatGPT. Struct I to assign to us to directly create a struct without a name and write it to another struct. That's such a bad phrasing. Cannot do this assignment from a temporary object. Ah, okay. Okay, it's as simple as that then. Oops. Syntax is slightly different. Cast the compound literal to the appropriate type. Unnamed temporary instance. Okay, I think that's more what I want, and that does seem to compile, or does it? Incomplete type, dang. What? How's that an incomplete type? What do you mean incomplete type? I'm literally using complete type is not allowed. "20-second break, be right back." Dang, okay. What is going on? Did I mistype it? Oh, yeah, I mistyped it. That's okay. Yeah, there we go. Okay, so that's like the not safe way to do it. So I'm constructing this struct into memory. And what's next? Okay, so I'm not handling a bunch of stuff right now. I'm not handle recursive situation. Maybe that's not hard. Void root. That all depends on whether we were already executing in the trap frame. Then the page handler itself is faulted. Start a new stack frame just under the current ESP rather than at UX stack top. Check whether it's in the range. Stack top. Yeah. Spool is. It's like it is already. Is recursive page fault. And that is if tf esp is greater than or equal to UX stack top minus page size. Yeah, UX stack top is page size. I guess I don't have a symbol that points there, so and this is going to be a pointer, right? Oh no, even pointer. Okay, that's going to work. And tf esp is less than u top. Yeah, utop is right there. So if ESP is greater than, wait a sec, yeah, or equal to that UX stack top minus page size, which is the first byte of this, and it is less than U top, then it's a recursive page fault because it was already operating. Would a better way to be to not say U top, but rather say ux stack top -1. Yeah, probably. That's maybe a little bit more resilient to changes in case I want to reorganize memory and put an additional thing above ux stack top that I don't need to change this. Root. It's a bad name, but I'll change it later. So if it is recursive page fault, then I want to do some special stuff. Otherwise, I just want to say it's here. And then now, root. Oops. Oh, okay. Root. And so it's P. So if it is a recursive page fault, then we want to place, then that would be the root, except we want to slightly add some space. So we're just going to hard code in a 4 or 4 bytes. I wonder, maybe size of int. Is that a bad idea? I'm going to call this dest u trap frame end. Not desk. Dest. Dest u trap frame end is there, then dest u trap frame is that minus the size of the u trap frame. Okay. So, yeah, so if it's a normal situation, TF ESP is not going to be in this range. It's going to be false. Therefore, we're going to use UX stack top as the end. We're going to compute the beginning of the struct from that, and then we assign into that. Otherwise, then if we're executing there and then that faults, the stack pointer is going to be within UX stack top minus page size and UX stack top -1. And then that's true. So then this is true. And then our end point is going to be the ESP that we arrived in this fault with, but with a little bit of extra space. We don't directly place it up to ESP. We say ESP minus a word size and then put it right below there. So I believe that's now handling the recursive case. 32-bit word. Now just the question, so I didn't even really get, now calling to the function pointer. This should hopefully be the easier part. But maybe not. Now I need to drop back into user space, but out of a specific place. So, okay. The most obvious way to do this is mutating the trap frame. But wait a sec. env run. How does this work again? Takes an environment and then drops into it, specifically using its trap frame. So what I can do, which I don't really love, but I can mutate the TF to direct to EIP of the handler. Ah, right. Right, so it's like TF EIP equals upcall. No, equals this. No, cur env upcall. And then I set, what do I set the ESP to? I set the ESP to dest u trap frame. Dest u trap frame. Which achieves the desired memory layout here, where ESP points directly at the start of the trap frame. Let's see, is that? And then we call env run this, no, cur env. We drop back into cur. Is that correct? Somehow I'm actually not sure if that's correct, because I'm kind of wondering, how does this thing, what happens after here? We return, right? And I want it to return right. That's right. So this thing by default does this. It drops back into current environment. So I don't think I actually need to explicitly do this. Not actually necessary. What is this return? Is it this return? It's a void. It's void. Back to anyway. Although maybe it's a little bit nicer and cleaner just to do this, because otherwise we are kind of relying we're just kind of relying on this to be there. Which is okay, but there's nothing bad that happens by doing this explicitly. That's the way, that's the end of the interrupt handler. We've done everything we needed to do, and we need to do something else. We can either just drop back in the process, start running it, or drop into the scheduler and find something else to do. But really, we're done here, and so this is just time to say goodbye and figure out what to do. And so dropping into the environment is a totally acceptable thing to do. There's no special cleanup that needs to happen, and it's not a problem if we decide to do it earlier. So I think I will do that. It's always the kind of the tricky thing here. This thing is annotated, I guess, with the no return. I wonder if I will get a compiler warning. Okay, not quite yet. these are all what? Event pointer T. Okay. Makes okay, without cast. This thing. I need to cast both of these places, which is kind of annoying. What if I just did that here? Sick. Okay, that works. I did not get any kind of error, though, from adding code after a no return, which I kind of am sad about. So I'm going to keep this comment here. Env run doesn't return. Okay. So I'm doing all of this stuff except for the safely part. What is the safely part here? I'm writing, what happens if the user environment runs out of space on the exception stack? It can run out of space in such a way that when we compute this, we fall off the end and potentially trigger a page fault from kernel mode, which we don't want to do. So maybe technically, I forget, check, or no, it literally told me what to do. User mem assert. Ah, right, I am not using that enough. Checks that the environment env is allowed to access the range of memory. If it can, it returns. If not, then it's destroyed. And this thing does not return. What happens? We hit the scheduler, right? Okay. We hit the scheduler. So or can't. This is the only thing I'm thinking about. So we're from the kernel, we are about to do a memory write into some place. Which is either UX stack top or potentially somewhat arbitrary. But before we got here, we've already done some checks. We've already validated. So in the case of UX stack top, we've already validated that it exists and it's writable. So we are safe in that case to just go ahead. So here's what I'm thinking. So it all comes down to ESP basically. That's the user controlled data that we are using to determine our memory right. And so maybe some kind of other check, like if user mem assert kerenv esp tf esp. Right, so this is some kind of region of memory. And so we've already checked if an overflow happened. So clearly that didn't quite happen yet, but it's possible for user space to consume 100% of the exception stack, but not overflow it just yet. And then trigger a page fault somehow. But then like right before it triggers the page fault, it reroutes ESP to point somewhere malicious or something like that. And if we did not do these checks, we would be like, okay, it has function pointer, it has this piece of memory mapped and writable, it has not overflowed the exception stack, and this is interesting. In order to use the ESP for this write, actually ESP is constrained. ESP must be within that region. But maybe it's very low. Maybe it's actually at the bottom. It didn't overflow, like nothing has overflowed just yet, but ESP is dangerously close to the bottom. Okay, 20 seconds, be right back. Maybe ESP is dangerously close. It's right at the border. It's, I don't know, it's right at the bottom of the exception stack. And then therefore, where that's gonna see it's a recursive page fault. What happened? Oh, okay. It's a recursive page fault. It's going to compute the end, which might already have crossed the boundary. It's going to compute that even lower to get the struct start address, and it's going to do a memory write. And it's possible for that to be in the empty memory zone, which is going to be a kernel page fault from kernel mode. Which we want to avoid. So, I don't know. Is it actually, we're trying to dest u trap frame size of dest u trap frame pt writable, right? Something like this. Before we do the struct write, which is kind of a large write, we are going to validate that this region that starts from dest utrap frame up through the size of it is writable, because that's how that works, right? pass in the VA to len, and it automatically puts in user space. It's allowed to access that memory with present user space, and in this case writable. And if it can't find it, which would be here, if it's not present, we fail. And report this global, do something with this global variable, and which we just use for the print, I think, and then we crash. Then we not crash, we kill the process. So yeah, I think that handles the safely part. Okay, that's kind of cool. That feels somewhat hardcore. This is like some serious, this is like actually a bit of serious kernel hacker type of stuff. Yeah, we're kind of like mucking with registers, we're diverting execution to this temporary place, handling recursion. Nice. No idea if the code works. I hope it does. But yeah, sounds about time for a git. Oh, I need to do something about this color scheme. That is utterly unreadable. Okay. Size 9. Impl. And safety checks. Okay. Cool. Moving forward. Next, you need to implement the assembly routine that will take care of calling the C page fault handler and resuming execution at the original faulting instruction. It's the handler that will be registered with the kernel using this thing. Okay. So now we're going to this thing. Implement this thing. The interesting part is returning to the original point in the user code. You'll return directly there without going back to the kernel. The hard part is simultaneously switching the stacks and reloading EIP. 8, okay. Page fault, upcall entry point. This is where we ask the kernel to redirect us. Okay. Kernel switches our ESP to point to the user exception stack, pushes it onto the stack. This is the request call that will reserve for us a blank word above the ESP for scratch work. We then have to call up to the appropriate page fault handler and C code pointed to by this global variable. Okay, push ESP because this thing presumably it takes a pointer to the utrap frame, so we push that argument, then for some reason move that into EAX, indirect call into EAX, And then okay, that runs, returns. We can pop that thing we just did, and now it's time to return. Okay, to return, you must return to the trap time state. Push trap time EIP onto the trap time stack. So that is the interesting part. We're trying to jump or like return back to the instruction, but like, why is it not possible? Like, how do we even do that? What information do we have? We have this utrap frame, which is just all this information, this critical information about, so we need to return to the EIP and reset the ESP. And this stuff is, oh, actually we need to restore all of this actually. We can't return directly. We can't call jump, since that requires us to load the address into a register, and all registers must have their trap time values after the return write. So when we arrive at that instruction, everything needs to be perfect. Yeah, and so we can't hard code, like we obviously can't hard code the jump address. It's going to be in different places. It's going to be dynamic based on this EIP. And so you could imagine we like load EIP into EAX and then jump to EAX or something. But then when we arrive at that instruction, EAX is this weird pointer, and it's not the actual value that it should have. So can't use jump, can't call ret, because then ESP would have the wrong value, which is interesting. Because with ret, that pops something off the stack and then jumps to it, but then ESP is in this weird place. It's on the exception stack. So what we need to do is push something onto the trap time stack and then ret from there, which restores the stack pointer to be exactly in the right place where it needs to be. I see. In case of the recursive fault, we actually want to recurse back to the handler that was previously on the exception stack, I think. Right, and that's where this empty slot comes in, because yeah, like we have been recursing on the exception stack. We want to go back to executing on the previous stack, and we need to restore, it's the exact same thing. We need ESP to be directly back where it was at the time of the previous handler, and all of these constraints still apply. And so the workaround is exactly the same. In either case, we put the value to return back to the EIP directly below the last place directly below the stack pointer value when the fault happened, either in the trap time stack or on the exception stack. We put this thing right below there and then do a ret, and that we make sure all the other registers have their state, and we place that EIP thing there, we ret, and then the ESP is in the perfect place to return, which makes sense. It's pretty clever. Throughout the remaining code, think carefully about registers available for intermediate calculations. You may find that you have to rearrange your code in non-obvious ways as the registers become unavailable as scratch space. Okay. Restore the trap time registers. After you do this, you can no longer modify any general purpose registers. And how do I do that? There's this, it's like pop, is it pop AL or something? Yeah. So ESP points at a trap frame here, basically, which starts with the push regs. So we pop AL, the push regs. But in the U-trap frame, they are not at the start. We actually need to adjust ESP a little bit higher, I think. So first step, adjust ESP by 8 bytes, then do a pop AL. Then restore E flags. Okay, not totally understanding what the strategy is here, because EIP EIP is in the way. So we pop AL and that puts ESP there. We can't use any general purpose registers. Can no longer do any arithmetic operations. So, wow, okay, that is like kind of tricky. Switch back to the adjusted trap time stack. So this is kind of obvious. It's going to be a ret. This is the challenging bit. This is a fun challenge though. So we actually need to place the EIP based on the ESP here. And then ret. But ESP is currently pointing here. I don't know, the first thing we need to do is add and how do you even add ESP? What was it? It's like add ESP4. I have no idea if that's correct. I need to find some other code to reference tree.s. S in the kernel. Or wait a second, no. Trap entry s sp. Or actually, was it env pop CF? Okay, add L for ESP. All right, take that as an example of how to do this. L8 pop CF fault VA CF error, then pop AL, restore trap time registers. So this thing's on the stack, our ESP points at it. We advance up 8 bytes. We pop AL. Okay, EIP. We now point at EIP. I can no longer use any general purpose register, so maybe I need to even do this earlier. But the thing is, need to point ESP at the EIP we pushed, right? That's the last thing. Rearrange your code in. So is this ordering a red herring? As registers become unavailable. I think they might be leading me astray a little bit here. Okay. Wait, working backwards, we definitely have to ret. Before we do the ret, the EIP needs to be in place and the ESP needs to be in place. After you do the E-flags, you cannot do any math. So that needs to be after this at least. The question is, how do we point ESP? How do we know where to point ESP if we don't have any registers to store something into? Okay, this is okay. 20 seconds. I'm running out of time. Yeah, we might need to resume this next time. But yeah, this is actually pretty exciting and a pretty decent challenge. Restore E-flags from the stack. How do you... what's the instruction? Instruction for restoring E-flags. Pop FD, right. Actually, yeah, wait a sec. What is like the trap frame? Flags are ways far apart. So here we set ESP to point at the trap frame. We pop the registers, pop ES, DS, skip the trap num, and IRET to this thing, which automatically does all the stuff, right? So at the very least, how do we do these moves? Also, we have no general purpose registers here. What do we even have? Well, we have memory. That, I mean, yeah, maybe we should be using memory a lot more. We can totally use memory. Right. Yeah, like there's no reason we can't use memory, right? So maybe that's the answer. We're just going to then I'm going to, so we have this EIP on the stack. The kind of tricky part is we need to sort of reorder these two things. I don't understand why this ordering is like this. It's just making our life hard, I think. The fact that EIP, I'm just gonna sketch it out. So so we can't use any general purpose registers. So we move is P plus 4 bytes up. Do a pop. We could do a pop FT, but then we can't do any more math. So I feel like, yeah, memory is definitely going to be the way to go here. So after we do the pop FD, we can't do any more math. So it's after we do the pop FD, we basically just want to do pop something into ESP probably, and then ret. Yeah, that's the way we're going to do this. It's going to be like some kind of pop. ESP. I don't know what the instruction is. It's like pop L or something. I have no idea, but we're gonna pop. We're gonna pop the appropriate stack pointer into ESP. The EIP already needs to be in the right position. So I'm just kind of working my way backwards. So now in order for this to work, EIP needs to be written to right position. Stack needs to look like E flags ESP. We pop FD, we pop ESP and ret. So something along the lines of, I'm going to even say before here, even before we start doing anything, move EIP into memory at ESP. Or to do it more. Something like this is going to be, we're going to write the EIP into memory directly below the ESP. We can just do all that with temporary registers or whatever we need to Maybe we don't even need them. Then we do our addition, pop all the registers out. And then yeah, but then we need to prepare this stack to look a specific way, which might be difficult. So maybe we just do a bunch of stuff up front. We move things into, we just move it into memory very early. Then we maybe prepare. Basically the whole problem, like this thing is like not ordered in a way that's very helpful. Yeah, why is this ordered the way it is? I kind of feel tempted to reorder it. But so the stack needs to look like this. We need to somehow push E flags, push ESP. So can we something like this? I'm not gonna have time to like do this, but I'm gonna sketch it out so I can resume this next time. So after we pop all the registers, then we're just going to push at ESP plus 8, push ESP again, push ESP plus 4, push E flags. So this constructs this stack state that we need. So yes, we're gonna add 8, pop these things. We're going to then push 2 more things onto the stack. We're going to push the E flags and then push the ESP, push the E flags. Then we're going to pop E flags, pop ESP, and ret. Okay, I'm gonna leave it there as a cliffhanger. We'll fill that out next time in week 43, actually. So that's it. Thanks a lot for watching. Subscribe to my channel if you liked this kind of content. I have a Discord server, which I'll link in the description. Feel free to join that. Leave a like, leave a comment, and yeah, thanks. I'll see you next time. Bye.